Hello, my name is Ashley Bluemel, and I worked with Dr. James Donaldson to complete my senior thesis, entitled Synthesis of a 1,4-fluorobenzyl 4-naphthalene 2-aloxymethyl 1H123-triazole for potential autism treatment. I decided to do this project as my senior thesis for a couple of reasons. One reason was that I'm a biochemistry pre-pharmacy major here at Missouri Southern, and I wanted to do some sort of pharmaceutical research for my thesis. I was specifically intrigued by the idea of autism therapy because one of my childhood friends, as well as both of her brothers, were at different points on the autism spectrum, and the differences between my life experiences and theirs always intrigued me. I wanted to find some way to bring our experiences closer together, and this project was a great way for me to do that. With the bare-bones idea of doing some sort of autism treatment research, I took to the internet, researching previous autism treatments, symptoms, causes of symptoms, and the like. I found that there were many points on the autism spectrum, and that many symptoms and ailments are considered autism spectrum disorders, ASDs, or pervasive development disorders that I previously thought were their own separate ailment, ranging from specifics like Asperger's syndrome to a more general classifications, such as pervasive development disorders not otherwise specified, otherwise known as PPDNOS. ASDs are generally classified by the presence of three features: qualitative impairment of social interactions, stereotypical behavior, and impaired communication. Many subtypes or symptoms can fall into these categories, including hyperactivity, inattention, irritability, repetitive behaviors, and discomfort with verbal and nonverbal communication, among many others. Previous treatments for ASDs have generally been focused on symptom management, which can include a multitude of medications, including but not limited to methylphenidate, guanfacine, or atomoxetine for hyperactivity or inattention, risperidone or aripiprazole for irritability, fluvoxamine, citalopram, or fluoxetine for stereotypical behaviors, and lamotrigine, amantadine, memantine, and oxytocin for core social impairment. These medications have had varying levels of success, but have also seen as many as almost 20% of participants in clinical trials dropping out due to side effects. Because many symptoms are present in a single case of an ASD, many patients are on multiples of these medications, which can be very expensive for patients and their families, as well as very time-consuming, because different medications must be taken at different intervals. The goal of this project was to create a potential treatment for ASDs that renders the need for multiple medications obsolete, because instead of treating symptoms, the cause is being treated instead. This project employed the hyperglutamate theory of autism, which states that the overabundance of the neurotransmitter glutamate in the brain and cerebral spinal fluid causes an overstimulation of glutamate receptors, which causes many subtypes and symptoms of ASDs. Glutamate is found in such large quantities in the brain because of a genetic mutation in the gene that codes for glutamine synthetase, which converts glutamate, the active form of the neurotransmitter, into glutamine, the inactive form. This overstimulation leads to many ASD subtypes, including obsessive compulsive disorder, OCD, anxiety, and depression, to name a few. Using the hyperglutamate theory of autism, the known allosteric glutamate receptor inhibitors were examined, as shown in the top image. The specific receptor that I researched was metabotropic glutamate receptor 5, generally referred to in the literature as mGluR5. Metabotropic means that this specific receptor was used in the metabolism of glutamate, and it is the fifth such receptor. I chose to use this specific receptor because previous research has been found to successfully inhibit this receptor, but not to the efficacy necessary for FDA approval. Looking at the similarities between the known inhibitors of mGluR5, we created the bottom target molecule, specifically using dipraglurant as the model. The red indicates a large aromatic group, the green indicates a substituted aromatic group, and the yellow indicates a fairly rigid central connector that allows for little to no rotation around bonds. This synthesis was composed of three individual steps. The first step was an SN2 reaction that combined 1-naphthol and propergyl bromide, which yielded 2-prop-2-ene 1-aloxynaphthalene. The next step was the synthesis of 1-azetomethyl 4-fluorobenzene by treating 4-fluorobenzyl chloride with sodium azide. The final step of this project was the combination of 2-prop-2-ene 1-alloxynaphthalene and 1-acetomethyl-4-fluorobenzene in the presence of copper sulfate to create the 1,4-fluorobenzyl-4-naphthalene 2-alloxymethyl 1H123-triazole. While the first reaction step proceeded with a relatively high yield and the second reaction step was assumed to have gone to completion, the final combinatory step was revised multiple times during synthesis. It is important to note that due to the explosive nature of sodium azide, exact yield was not able to be determined for the second step. The initial attempt at combination used the 2-prop-2-ene 1-alloxynaphthalene and 4-fluorobenzyl chloride in the presence of sodium azide and copper sulfate using a 50-50 mixture of water and tert-butanol as the solvent under microwave conditions. The use of the water and tert-butanol as the solvent yielded very little mixing between organic and aqueous layers, which is necessary for reaction completion, and thus the first adjustment was made. The second attempt at combination used the same process as the initial attempt, save for the use of ethanol as the solvent instead of the water tert-butanol solution. Ethanol has both a polar and a nonpolar side, allowing for the solution to be conducive to mixing immediately. The final attempt at combination combined the 2-prop-2-ene 1-alloxynaphthalene and 1-acetomethyl-4-fluorobenzene in the presence of copper sulfate and L-ascorbic acid, using ethanol as the solvent once again. This reaction was then left to reflux overnight. Reaction progress throughout synthesis was done using thin layer chromatography, with mobile phases varying from 5 to 30% ethyl acetate and hexane. In the figure on the left, the third attempt at combination was ran against the reagents, the 2-prop-2-ene 1-alloxynaphthalene and 1-acetomethyl-4-fluorobenzene, respectively. The presence of the spot along the blue line indicates that some of the 2-prop-2-ene 1-alloxynaphthalene was left unreacted, while the absence of the spot along the red line indicates that all of the 1-acetomethyl-4-fluorobenzene was used. Because the 1-acetomethyl-4-fluorobenzene was the limiting reagent, this reaction was determined to have proceeded to completion. Before analyzing the reaction products using spectrometers, the reaction product for attempt 3, noted in the middle figure as R, indicating that it was refluxed, was ran through a chromatography column that used a silica packing and a 10% ethyl acetate and hexane mobile phase initially. Once the most polar compound had ran through the column, indicated in purple, the mobile phase was increased to 30% ethyl acetate and hexane. This change was performed to allow the final two spots, indicated in orange and pink, to separate as much as possible while in the column. Each of these spots was then found in the aliquots, indicated in the figures on the right, and analyzed using spectrometry. The first aliquot analyzed using NMR spectroscopy was the 2-prop-2-ene 1-alloxynaphthalene, using deuterated chloroform as the solvent. Deuterium is an isotope of hydrogen, consisting of 1 neutron, 1 proton, and 1 electron, respectively. Hydrogen, while similar, differs from deuterium in that hydrogen only has 1 proton and 1 electron. The additional neutron allows deuterium to appear invisible to the proton NMR, which allows the proton locations in the target molecule to be determined. Using the peak in green as the integration baseline, we are able to determine how many protons each peak represents. The green peak is used for the integration baseline because it is easy to find based on the fact that it is the only peak of its kind. There is also only one possible location in between the peaks that represent the outsides of the molecule, thus making it easy to determine how many protons this peak represents. The peaks indicated in red are determined to be the hydrogens surrounding the naphthalene group because of their close proximity to one another. Conversely, the peak indicated in purple is determined to be the alkyl proton because of its diminutive presence. It is also important to note that the peak indicated in yellow is the internal standard for deuterated chloroform, used to ensure that locations along the spectra are accurate. By adding the number of hydrogens that each peak represents, the total number of hydrogens in the compound can be determined. In this case, they are determined to be 9.25 hydrogens, but because there cannot be a partial hydrogen, we round up to 10. This matches with how many hydrogens that are expected to be in the molecule, indicating that this reaction was a success. The second aliquot was analyzed next. Instead of deuterated chloroform for the solvent, dimethyl sulfoxide was used because of the decreased polarity of the target compound compared to the polarity of the previous compound. Using the peaks in green as the integration baseline, the total number of hydrogens in this compound was determined to be 15.63, rounding up to 16, which was the expected number of protons in the compound. Using a similar method to the previous aliquot, the relative positions of the peaks between 7 and 8 parts per million indicate that they represent the protons surrounding each aromatic group, both of which are indicated in red. The peak indicated in pink is determined to be the only insinuated proton on the azetobenzyl group, also indicated in pink. This is able to be determined because of the relative position of the proton between multiple electron-dense groups. It is also important to note the different location of the internal standard. For deuterated chloroform, the internal standard was located at 0 parts per million, while in dimethyl sulfoxide, the internal standard is located at approximately 3.3 parts per million, indicated here in yellow. The third and final aliquot was analyzed in deuterated chloroform initially, followed by analysis in dimethyl sulfoxide. In deuterated chloroform, the separation between peaks originating from the different aromatic groups were difficult to deduce, which led to the use of the dimethyl sulfoxide. This inability to distinguish between peaks and their locations was decidedly due to the decreased polarity of the compound and the increased polarity of the solvent, a mismatch that was quickly remedied. Despite these hurdles, a couple of peaks are still able to be determined, specifically the dual peaks indicated in green. Looking at the spectra for the final aliquot in dimethyl sulfoxide, each peak is able to be matched with its originating hydrogen. First, the peaks in green can be determined using integration and previous spectra locations. Next, the peaks in red can be determined to be the hydrogens surrounding the aromatic groups on both ends of the compound, also indicated in red. The total calculated number of protons for this spectra is 13.53, or 14 protons, compared to the expected 16. This indicates that at least 2 hydrogens are being filtered out by the NMR due to insufficient peak height. It is important to note that these filtered peaks could include the azetobenzyl proton and/or the 2 aromatic protons that are missing. Because of the classification of COVID-19 as a pandemic in mid-March, all classes at Missouri Southern were moved to the distance learning format, which came with its own set of challenges. Because of this change, optimization of each step of synthesis was halted, as well as the ability to obtain carbon NMR data, as well as any infrared spectra data. Looking back at the last year and a half of research, I think the most important thing that I'm taking away from this project is the details that go into pharmaceutical research. Before this project, I wanted to be a retail or hospital pharmacist. Now, however, I'm looking forward to looking more into the research pharmacist positions and the good that I can do from that position. I look forward to working in the Chapel Hill, North Carolina area and getting to participate in the research that goes on in Research Triangle Park nearby. If I got the chance to do this project all over again from the beginning, I think I would begin much sooner so that I could get as much time working on optimization of the techniques as possible. As far as furthering the research that I've started, the optimization of the microwave technique would be of the utmost importance moving forward. Upon creation of the library of similar molecules that could potentially treat ASDs, movement from research to implementation should commence. Despite all of the struggles that the last year and a half has brought, I'm extremely proud of the work that I've done and look forward to implementing all that I've learned during pharmacy school and my career. I would like to acknowledge a couple of people for their contributions to this thesis, specifically the Missouri Southern State University Chemical and Physical Sciences Department, the Missouri Southern Honors Program, Kent Brody for making sure I could work in the lab each day, Jacob Reimer for giving up time with me and encouraging me to complete this project, the Bluemel and Donaldson families for forfeiting time with their loved ones for the completion of this project, as well as Christopher Provins, Brandon Kerr, and Blake Overman for their previous contributions to this project through previous research.